The future of manufacturing is being written today. It is a future filled with smart factories, intelligent machines, incredible efficiency. This new era is often called Industry 4.0. At the heart of this revolution is the digital twin. Imagine creating a perfect virtual copy of a physical object, like, say, a jet engine, an entire factory floor. This digital copy is not just a static three-dimensional model. It is a living, breathing simulation constantly updated with real-time data from sensors on its physical counterpart. This allows companies to monitor, analyze, and predict performance without ever touching the real thing. However, this powerful technology comes with a significant challenge. The value of a digital twin is entirely dependent on the quality and trustworthiness of its data. If the data feeding the digital twin is inaccurate, corrupted, or tampered with, the simulation becomes useless. A digital twin is much more than just a computer-aided design model. Think of it as a dynamic, virtual replica of a physical asset. This asset could be a single component. It could be a complex machine, like a wind turbine, or an entire production line in a factory. This virtual copy is connected to the real-world object through a network of sensors. Those sensors are part of the Internet of Things. They continuously collect data about condition and performance. Data example: temperature. Data example: pressure. Data example: vibration. Data example: output levels. Operational status, all streamed in real time. The point: the twin behaves like the physical counterpart. If a part overheats, the twin shows the same rise. That creates a powerful tool for monitoring and analysis. Engineers can see what is happening with the real machine even thousands of miles away. They can see performance and efficiency, spot emerging issues, and predict outcomes. But it all depends on data integrity. Garbage in, garbage out. To understand how we can secure digital twin data, we first need to understand blockchain. At its core, a blockchain is a special type of database, a distributed digital ledger. Unlike a traditional central database, a blockchain is copied and spread across many computers. This decentralized nature is its first layer of security. Because there are many identical copies, it is incredibly difficult to alter records. A hacker would need to attack most of the network at once. Practically impossible. Data is recorded in blocks, each containing entries. Once filled, a block is linked to the previous using a cryptographic hash. Each hash acts like a unique digital fingerprint, creating a chain of blocks. This structure makes the ledger immutable. If someone alters an old block, its hash changes, breaking links, and the network rejects it. Every transaction is permanent and viewable to those with permission. This transparency builds trust. Everyone sees the same unalterable truth. A sensor reading on-chain is authentic and unchanged since recording. No central authority needed, the network validates entries. Decentralization, cryptographic linking, transparency. This is why blockchain is revolutionary for trust. It provides mathematical guarantees, perfect for closing the digital twin data trust gap. The primary role of blockchain in digital twins is to serve as a secure, immutable logbook. Think of every temperature, vibration, and pressure reading as a transaction. Each data point is written into a block, sealed, and linked to the previous. No one can secretly alter a past reading. The network would detect it. This creates a golden thread of data integrity for the digital twin. Because on-chain data is trustworthy, the twin becomes more reliable. Imagine a pharmaceutical line where medicine quality depends on precise temperatures and mixing speeds. By logging all sensor data to blockchain, the manufacturer can prove perfect conditions throughout. It provides an unbreakable audit trail for regulators and quality assurance. From raw materials to assembly and shipment, every step can be recorded. Installations and maintenance reports feed the twin with a verifiable history. This history helps understand the past, diagnose the present, and predict the future. The digital twin is no longer a snapshot. It is a living history book. In aerospace, a twin shares trusted data between airline and manufacturer, enabling proactive, safer maintenance. They replace parts proactively, enhancing safety and reducing in-flight risk. Modern manufacturing is rarely the work of a single company. It involves a complex network of suppliers, partners, logistics providers, and customers. For a digital twin to be effective, it needs data from across this ecosystem. For a car twin, origins and specs of parts like the battery and tires. But sharing data is challenging due to security, privacy, and control concerns. Blockchain enables secure and transparent collaboration. Partners can join a shared, permissioned blockchain where only authorized parties contribute data. Everyone sees the same truth, but only the information relevant to them. The battery supplier logs manufacturing date, composition, and tests on-chain. Installation is recorded. Usage logs charging cycles and performance. Manufacturing to real-world use, one secure chain. Complete history improves life prediction and charging recommendations. If a defect appears, trace affected batches instantly. Recalls become faster, more precise, and less costly. All partners see real-time status, breaking down silos for richer twins. Blockchain offers more than secure storage. It enables smart contracts. A smart contract is code on the blockchain that executes when predefined conditions are met. Think of it like a digital vending machine. Condition in, outcome out. Execution is transparent, irreversible, and tamper-proof. In manufacturing, smart contracts automate tasks end-to-end. A twin predicts a part will fail in 48 hours. That prediction triggers a smart contract. It places a replacement order automatically, schedules a technician, and updates the production schedule. Shipment and receipt are recorded on-chain, and payment releases automatically upon confirmation. No human intervention, fewer delays and disputes. If QC detects deviation, a contract can halt the line and flag the batch instantly. Encode business logic on-chain, and systems self-manage in real time based on trusted twin data. Processes get faster, more efficient, less error-prone. Smart contracts plus digital twins create a responsive, autonomous manufacturing environment. The vast amounts of data collected by digital twins are incredibly valuable. They provide deep insights into real-world performance. Traditionally, this information remains locked inside. Other businesses would pay for access: insurers, researchers, and other manufacturers. For example, insurers could analyze how driving behaviors affect wear to price policies better. The challenge: sharing or selling data without losing control or risking misuse. Blockchain enables a secure, transparent marketplace for digital twin data. Grant access to specific datasets for limited time or purpose, governed by smart contracts. Example: anonymized data from 10,000 turbines for 6 months, with automatic access on payment and automatic revocation on expiry. Every access is auditable and immutable. New models emerge. Sell performance as a service based on uptime and efficiency, tracked by twins and verified on-chain. Or sell performance data to partners developing complementary products. Secure, transparent, automated. Blockchain turns digital twins into revenue-generating assets, all while keeping full control of intellectual property. The rise of Industry 4.0 and the Internet of Things has connected factories like never before. This enables incredible efficiency through digital twins, but creates new vulnerabilities. Every connected sensor, machine, and controller is a potential entry point for attack. An intruder could manipulate data, feeding false information to twins and risking bad decisions or sabotage. Blockchain acts as a powerful layer of defense. Its decentralized, cryptographic, immutable design resists tampering. When data is written to blockchain before reaching the twin, it becomes a trusted source. Even if a network link is compromised, historical on-chain data cannot be altered. Malicious inconsistencies are flagged immediately. Blockchain can secure device communications in peer-to-peer networks, logging each command as a transaction. Every command is authenticated, authorized, and logged. A shutdown request is validated by the network before execution, blocking unauthorized actions. This security is essential for trust in automation. Secure device data and validated commands build factories that are smart and highly secure. It protects assets, intellectual property, and worker safety at scale. The journey into Industry 4.0 is a quest for a smarter, more efficient, more connected world of manufacturing. Digital twins offer unprecedented monitoring, analysis, and prediction, but only if the data is trusted. The persistent data trust gap has limited their potential. Blockchain provides the missing ingredient, a foundation of absolute trust. By creating a decentralized, immutable, transparent ledger, blockchain ensures every twin data point is secure and verifiable. It transforms a vulnerable flow into an unbreakable chain of evidence. The twin becomes a reliable mirror of reality across the entire asset lifecycle. It redefines collaboration on a shared, trusted platform. It automates complex processes with smart contracts. It opens new revenue streams, and it strengthens cybersecurity. To lead in Industry 4.0, embracing blockchain and digital twins is essential to build the intelligent, autonomous, resilient factory of tomorrow.